Hello, welcome to XPE for Yearly Thermal Analysis Quick Take. Today I am going to talk about various aspects of thermal analysis using Xilinx Power Estimator. Just to recall, Xilinx has been very successful at improving performance per watt with every generation. More importantly, relative to 28 nanometer, Zinc UltraScale Plus delivers 2.4x fabric performance per watt, 3x higher series bandwidth, 4x DSP bandwidth and 8x larger on-chip memory. The fact that our devices are more than double in size, performance increases at more than a speed grade and gigabit transceiver data rates continue to climb. We would need to cut power by approximately 75% each generation to keep up with the size and bandwidth improvements and keep overall power relatively flat. On the other hand, as process node continue to shrink, FPGAs become more complex and power increases the control of component temperatures. Higher power in a smaller package footprint. This results in overall power density increasing for every generation and means customers now need to work on addressing FPGA cooling in their system. Thermal is everywhere and it has become more critical to successful designs. The FPGA design and system reliability as well as electrical functionality and performance are determined by the operating temperature under which all logic functions. Die temperature must be controlled because it impacts the timing, leakage power, package design and lifetime of the device. Circuits run slower when they are hot and their lifetime reduces exponentially with increasing temperature. Furthermore, leakage power increases exponentially with temperature, which can cause a thermal runaway. All these factors have forced chip manufacturers to employ techniques to control the die temperature. It's very important to consider and deal with thermal challenges early in the design cycle. Xilinx Power Estimator has capabilities to allow customer to better understand and track FPGA junction temperature throughout the design process to ensure junction temperature does not become an issue late in the design cycle. Let's look at it in detail. The best way to assess thermal characteristics of a device package is selecting predefined and commonly known environmental and thermal management techniques in XPE. Here is one of the automotive customer design estimation. In general, XPE users tend to set the maximum device junction temperature, which is 100 C for industrial and extended grades. Though it makes it more convenient to do so, you are actually masking the thermal characteristics of the package and end up estimating higher static power which will ever hit even at peak operating conditions of your application. Instead, set the right environmental conditions and let XPE calculate the maximum expected junction temperature. Ambient temperature is straightforward. For automatic application, you can set it to 55 C. Rest you can keep it at default unless until you have reasonable understanding of the design environment conditions. Medium heatsink profile and medium board size selection are typically used. Now, XPE calculates the junction temperature based on total power and environment setting, which would be ideal result. As you can observe, right away more than 30% power saving compared to maximum device temperature setting. If estimated junction temperature is less than maximum operating range, you can observe additional power benefits of operating at cooler temperatures. And also, you can easily see how much more power can be dissipated in the device at expected environmental conditions. Thermal margin shows additional temperature and power headroom available within the current device package selection. This helps you to choose the right device and package for your application with less thermal challenges and minimal cost. So, try not to set the maximum device operating temperature. This is mainly used to assess the worst case situation for board designs and solutions. Xilinx flip chip packages are designed to minimize thermal resistance and maximize power dissipation. However, some applications dissipate more power and require external thermal solutions. Proper thermal design is generally depend on the heatsink utilized, the airflow and the thermal interface material used to enable efficient transfer of the power dissipated by the device to the heatsink. XPE enables our customers with basic thermal analysis for a less challenging thermal environments. This is the simplest approach to quickly assess the thermal margin with the current thermal solutions. So you could just read the manufacturing spec of heatsink and thermal interface material and feed them into the XPE. For example, assuming 250 LFM airflow, the thermal resistance of the heatsink is 10 C per watt from the manufacturer's specification. Typically, these numbers are based on JEDEC standard values and varies according to real system environment. For initial analysis, we can use the same number for now. Also make sure the ambient temperature and board settings are adjusted too. Observe the estimated junction temperature by XPE and make sure it is not close to or above maximum device operating limits. Also, XPE thermal margin indicates how close the estimation with respect to max limit based on the thermal solutions you applied for this design. If margin is small or negative, then need to take some action. Either go to advanced thermal analysis or improve thermal solutions. Could be effective heatsink, more airflow, etc. Note that uncertainty with this approach is much larger than advanced thermal analysis due to many factors. So it requires more thermal margin to sign off the thermal solutions based on basic XPE thermal analysis. In reality, it's very important to account all the aspects of board and system level environment conditions for accurate junction temperature and power density of any application. Thermal solution is the ideal solution for advanced thermal analysis. Thermal simulation requires worst case total power for the package, so force the junction temperature to maximum expected value. Most often that is max operating temperature of the device 100 C for extended and high grade, or customers in lower power design may want to target below TJ max in order to get improved power consumption. For given design, power should not exceed this calculated target. Then pass the total power results to thermal simulation. A compact thermal model is a behavioral model that aims to accurately predict the temperature of the package only at a few critical points like junction, case, and leads. The Delphi compact model is typically the best representative mode for packages and typically includes a representation of all the heat conduction paths. High predictive accuracy, portability, and computational efficiency make Delphi CTMs the most suitable for semiconductor manufacturers. That is what Xilinx intend to offer in support of package thermal analysis. These Delphi models is designed to be used with common resistor network solvers, CFD tools, and other system level thermal simulation tools, especially iSpec from ANSYS and FlowTherm tool from Mentor Graphics. Delphi models boundary condition properties allow users to use them with high degree of confidence for predicting junction temperature and heat fluxes. Typical junction temperature errors compared to detailed thermal model do not exceed 5%. Derive the effective junction to ambient thermal resistant value from thermal simulation. Now annotate XPE with more accurate local ambient and effective junction to ambient value as new environment settings. XPE recalculates the junction temperature based on thermal simulation results. Look at the results and ensure TJ max is not exceeded the operating conditions. Once you have the results, use XPE thermal margin to evaluate the thermal solutions. If you observe reduction in power, which also improves junction temperature, now you have confident on your thermal solution and also comfortable with additional thermal and power headroom available with the device. On the other hand, if you observe higher power, eventually higher junction temperature, you are quickly alerted with possible operating condition violations, such that you can go back to your thermal solution and improve it or work on power reduction on your design to bring it to more safe operating range. In a summary, definitely thermal management is more crucial to successful next generation designs. System reliability, performance, power, cost, and life factors are determined by operating temperature of the device. XPE enables early device temperature and power density estimation of packages and allows customer to better understand and track FPGA junction temperature throughout the design process. During device package selection, follow commonly understood thermal management techniques and try to avoid setting junction temperature to maximum device operating limit. For less thermally challenged design environments, read the thermal resistances of heatsink and thermal interface material from manufacturer's specification document and apply to XPE. Analyze thermal margin and take necessary action if the margin is still small or negative. For the medium to high power density system, perform advanced thermal analysis using Delphi models to estimate junction temperature and derive junction to ambient thermal resistance. Feed this theta JA value to XPE and analyze thermal and power margin. Take necessary thermal solution and power reduction technique to keep the device within safe operating condition. For more details, please contact Xilinx technical support or your local field team. Thank you for watching the video.